It's a handful of practice questions that you have on one of your handouts, and I'm just going to go through and talk about some of the answers for these. So the first question is asking, it says, imagine a place in the cosmos far from all gravitational and frictional influences. Suppose that you visit that place and throw a rock. What's going to happen to the rock in terms of its motion? Is it going to come to a stop? Is it going to go forever? With the idea of inertia, that if an object continues its motion unless a net force acts on it, once you throw the rock and get it in motion, in theory, it will just go forever and ever and ever. So it would just continue on. It wouldn't come to a stop. We have a 2-kilogram object moving horizontally with a speed of 4 meters per second. How much net force is required to keep it moving at this speed and in this direction? All right. If it keeps moving at the same speed and in the same direction, then its motion's not changing. It's in constant motion. And if it's in constant motion, then there's no net forces acting on it. So the answer for this question is, how much net force is required? 0. There is no net force that's going to be required to keep it doing what it's doing. All right, says Macintosh, you're arguing in the cafeteria. He says that if he flings the jello with greater speed, it will have greater inertia. Tosh argues that inertia does not depend upon speed, but rather the mass. Who do we agree with and why? Well, inertia, if we're looking at it with mass or speed, only deals with mass. So in this case, Tosh is arguing that inertia does not depend upon speed. So Tosh is correct about this. It only depends upon the mass. So the greater the mass, the greater the inertia. Speed is irrelevant when we're dealing with inertia. Question 4 says, supposing you were in a space in a weightless environment, would it require force to set an object in motion? If you were in a weightless environment in space, would you have to push something to set it in motion? Yes. So things still have inertia when they're in space because they still have mass. Mass and weight are not the same thing. Mass is still influenced by how much matter that something has, so we would still have to give it a net force to be able to get it into motion. Question 5 says, Fred spends most Sunday afternoons at rest on the sofa watching football games and consuming large quantities of food. What effect, that should be an E effect, if any, does this practice have upon his inertia? Well, if Fred continues doing this, he's going to end up getting more massive. And if he's more massive, then he would increase his inertia. However, if Fred is offsetting some of this, eating with exercise, he will keep his mass the same and his inertia would stay the same. But if his weight went up, then on Earth, that would have meant his mass goes up and his inertia goes up as well. Number 6 says Ben Too Close is being chased through the woods by a bull moose that he was attempting to photograph. The enormous mass of the bull moose is extremely intimidating, yet if Ben makes a zigzag pattern through the woods, he'll be able to use the large mass of the moose to his own advantage. So you may have seen this with animals before, where sometimes a small bird is attacking a large bird, and it looks like, that doesn't seem like a great idea. But the idea is the larger animal is going to be much harder to change its direction. So one of the evasive moves that sometimes smaller animals can use with larger ones is a zigzag pattern. Sometimes you see this with squirrels when they're running, that they come to a stop and they run. They don't just run in one direction, because if a larger animal is chasing them, it's going to be harder for that large animal to stop its motion and change its direction. So we see this in nature quite a bit. And finally, on number 7, it's a lot of reading here, but it says 2 bricks are on the edge of a lab table, and Shirley stands on her toes but sees the 2 bricks. She wants to know which of the 2 bricks is more massive. Since she is unable to reach high enough and lift the bricks, she could give them a push and discuss how the process of pushing the bricks would allow her to determine which 2 is most massive. So without lifting them, just by pushing them, she should be able to determine which one is more massive, because the one that is more massive will be much more difficult to move. If it's more difficult to move, that means it's got more inertia, and if it's got more inertia, then it's got more mass. So simply by pushing on 2 objects, if the surfaces are the same, we can generally infer which one is going to be the more massive, because it's going to be the one that's harder to push. Larger objects that are more massive are going to have more inertia. If they have more inertia, it's going to be harder to get them in motion.